Today we're going to talk about gravitational redshift again. So as we all know, when we have a photon generated by, for example, atom, the photon has a net rest mass of 0. Basically, it does not have a mass. However, photon has energy. For example, photon have energy if it has a frequency, omega 0. At the same time, Einstein said any particles its total energy should equal to mc squared. If that's the case, we can say, well, actually photons at frequency omega 0 will have a mass. Let's call this mass as m0. m0 should equal to E0 over c squared. In this particular case, should be h omega 0 over c squared. So that is the mass of the photon. Because c is very big, h is very small, so this is a very, very small mass, hardly noticeable. However, according to Einstein's theory, E equal to mc squared, photon must have this mass. What about another photon have a different frequency, for example, get 1? Then you will say, according to the same equation, we should say this different photons oscillate at a different frequency should also have a different mass. Right, this is based on the same principle. Now we're going to look at it, how this mass is going to be impacted by the presence of gravitational field. For example, if we have a building sitting on top of the Earth. Okay, this is the Earth's surface. This is the Earth's surface. So now, at the top of the building, for example, here, we can assume we have a device that can generate a photon. For example, it generates photons at the frequency h omega 0. Then what happens if I have an observer at the bottom of the building here, try to detect what energy this observer is going to see when it detects the photon come from the top of the building. And if in this case we'll assume the presence of gravitational field, so we have a gravity effect on any of the mass. So if that gravitational field is going to act on a mass here called m mass 0, and what happened to this mass? This mass is going to be impacted by g, and it's going to accelerate downwards to the bottom. And what is the energy it is going to gain when you come down from top to the bottom? If we assume the distance between the top and the bottom is h, then we know when the mass 0 going from top to bottom, it will gain additional potential energy. This potential energy should be m0 gh. So we know the original photons has initial energy h omega 0. So we are going to expect that by the time the photon come down to the bottom and be detected by the observer, the energy should equal to h omega 1. And this is the energy conservation law. If that's the case, then we can say, okay, h omega 1 equal to h omega 0 plus m0. What is m0? m0 we already know is h omega 0 over c squared. And we have g and h. So this leads to us this equation. Or we can say omega 1 now become bigger due to the gravitational impact. So omega 1 bigger than omega 0. Or another way around, we can say lambda 0 is bigger than lambda 1. Lambda is the wavelength of the photons. So that tells us at the top of the building, the wavelength is longer than when it is at the bottom. So if we send a light from the bottom of the building and shoot it up, this is a light, and if we send lambda 1 here, and when it was detected at the top of the building, you will see the lambda is received should be lambda 1. In this particular case, you will see the wavelength is redshifted by the time the light is reaching to the top of the building. This is exactly what was observed long time ago, and to verify Einstein's prediction. Although the wavelength difference is very small, in fact, it's only 2 parts in 10, 15 total. That's how small it is. However, even such a small difference in the wavelengths, and we can still detect it by the so-called Mossbauer effect. So this is one way to verify the gravitational redshift near the Earth's surface. Even if it's small, it's significant enough for us, especially for the modern communication industry, when we try to use global position system to locate our positions, because different wavelengths and will be used, and their changes when they travel from one place to another is become significant enough in order for us to have accurate prediction of our locations. So thanks for watching. This is another way to derive the formula for gravitational redshift.